Good afternoon, everybody, and welcome to this Talking Industry Extra promoted by TWI and KUKA on rotary friction welding. While you take your seats, we'll have a short video which is showing the process in general. Okay, I think we're ready to go now. Thank you for coming and taking your seats so promptly. Welcome to Talking Industry Extra on rotary friction welding. My name is Andy Pye. I'm consultant editor of Drives and Controls and a range of other publications and online publications from DFA Media. To start with, welding as a fabrication process has been utilized within manufacturing for decades. In this presentation, we will go through where friction welding and specifically rotary friction welding fits within the gamut of joining methods and also specifically welding. And to do that, we have 5 excellent speakers. I'm going to just briefly name them in reverse order. Jeff Price, Manager of North American Operations for Thompson Friction Welding. John Fisher, President and Operations of AFW, which is American Friction Welding. Nick McCarthy, who's Head of Sales and Market Development, AWS for KUKA Systems UK Limited. And Kate Franklin, the Senior Project Leader for friction and forge processes at TWI Limited. Between them, they will talk about the general process, the market opportunities, the business case, and also some of the metallurgy that goes behind characterizing rotary friction welding. But first and last but not least, I'd like to hand over to Jane Shimwell, who's the Technical Services Manager at KUKA Systems UK Limited, for a brief welcome. Jane.
Good afternoon, everybody, and thanks for joining us today for this Talking Industry spot. I'll begin by giving you my name. I'm Jane Shimwell, Technical Services Manager, and I look after the subcontract department at KUKA Systems UK Limited. KUKA is primarily known for being a robotics and automation conglomerate. However, there are several brands and companies that sit underneath KUKA and operate under their ownership, and one of which is Thompson Friction Welding. KUKA purchased Thompson Friction Welding from Rolls-Royce back in 1993. So KUKA have been had the ownership of the KUKA brand, the Thompson brand, for many years now. If you don't mind, I know that we don't want to really look at too many presentations, etc., but I would like to run some photographs as I speak, just so that you get an indication of the type of components that are routinely friction welded, and also the type of combination of materials. So I'm just going to share my screen for you, hopefully without any problems, and let it run as I speak. Okay. In Halesowen, we have a highly specialist team of approximately 100 people working in the friction welding business. They range from designers, commissioning engineers, service engineers, manufacturing engineers and spares, and we also offer subcontract friction welding. I joined Thompson back in 1994 as a fresh-faced communications graduate, and my career has developed through what I would call quite a long and informal postgraduate apprenticeship. I started on my first day in June 1994, and I've been here learning something new and interesting every day, 27 years later. A lot of people probably think that shows a distinct lack of imagination on my part, but friction welding is kind of a bug and we kind of get caught by it. From early on, I was attached to the subcontract department. I reported to the metallurgist, who was also the subcontract department manager. When he retired back in 2008, I took over management of the department. We have a team of people including machine operators, setters, a metallurgist technician, and a consultant metallurgist within the department. And we have the largest subcontract department in the UK, with several machines ranging from 15 tons capacity up to 150 ton capacity. And just to give you a kind of an indication of what that means in terms of capability, for medium carbon steel, we can join components ranging from approximately 4 millimeters diameter up to 110 millimeters diameter solid, tubulars up to approximately 220 millimeters diameter with a 25 mil wall thickness. We also friction weld many bimetallics. The capacity for those, the capability for those though is dependent upon geometry and also specific material combinations. Subject to component diameters, we can weld lengths up to 12 meters. We also have a fully kitted laboratory and prep room on site, which supports the subcontract work that we do, as well as enabling us to take in R&D work, investigation and analysis work for our machine customers. We offer procurement options, stock holding, pre and post weld processing, for instance, induction, stress relief. And really, one of the main drivers for us doing this event today is that most of us who are involved in friction welding are still so surprised that it's considered to be a niche process and a niche industry. There are so many engineers out there that haven't heard of rotary friction welding or linear friction welding. And really, friction welding probably touches nearly everybody's everyday life through one component or another. It's working its magic in the background. Friction welding components help to keep our lights on with power generation companies, and they keep the trains moving. Your car most likely has several components that are friction welded. It could be the axles, half shafts, the airbag canisters, the gear lever, the piston crown. Most people wouldn't realise this, but the time displayed on your clocks on your devices at home or your smartwatch will probably be received from timekeeping instruments in satellites, which will have friction welded components in them. The last concert you went to would have had cabling with friction welded connectors on within them. Netflix productions, they have sound recorded in equipment with friction welded components in them. We supplied components for the first Formula E motorsport charging ports. MRI scanners, they have friction welded cooling fins within them. buildings have friction welded rebar and steel stabilizers in them. The list is endless and could go on, but it just shows how prevalent friction welding is in the background of our everyday lives. In terms of the subcontract department and the work that we actually do at KUKA UK in Halesowen, we take working from companies that don't have budget for their own equipment, or they really don't want to produce their own friction welded joints. They prefer to use an independent friction welding specialist. Our customer base is very wide ranging, from safety critical and heavy and light automotive customers to mining and construction, oil and gas exploration, rail, power gen, medical, cryogenic, and many, many more. It's a very versatile process that can join many different types of materials. Over the years, we've seen the largest increase in demand for friction welding in bimetallics, so that's copper and aluminium connectors for power generation, cabling, earthing, entertainment, electrification of rail, with palms, cable lugs, deltoids, many other types of components. And we've also seen a huge increase in demand for cryogenic type material combinations. So that's kind of stainless steel, aluminium, or stainless steel to copper type of joints. The material combinations are very varied that are possible with this type of process and technology. And I hope that what you've seen today on the images and what you will hear and see from everybody else, all the speakers today, will really pique your interest and make you think about the type of components that you deal with on a daily basis, and whether this process could be of benefit to you for quality assurance and also cost savings. And with that, I would like to hand over to Kate, who is going to talk to you actually about the process. So you'll get much more of an in-depth technical evaluation of what the process actually is. So thank you for listening, and thank you.
Just quickly before we do hand over to Kate, I'd like to remind everyone that the chat is available to put in questions, and I see we're already getting quite a few. And in fact, one of them is being answered as we speak, which is excellent. So please carry on doing that, and we will answer them as we go or at any stage during and after the presentation. We've also had an inquiry from Neil, who's got a hearing problem. So we're trying to work out how to work with closed captions. We've not done this before. If we don't manage to do that, we'll make sure that you get a transcript of what is being said and a link to the on-demand version, so that you'll be able to get full value out of the presentation. And it's a note that we've made for future that we'll get on top of that problem for our future events. So with that, back to Kate, please.
Andy,
Yes,
I'd like to make a point. Jane brought up a very good point when she talked about a lot of growth in the dissimilar metals. I think that as a result of the material costs are starting to rise, and we do see that in our industry, that the biometals, the dissimilar metals really have an advantage with the friction welding process, because you only need to have the expensive metal, a smaller portion of it, and then a less expensive material elsewhere. So that is a great thing that Jane brought up.
Really good point, and we'll come back to that later on as well. Okay, Kate, it's all yours.
Thanks, Andy. I'll just quickly introduce TWI Limited. So it's a world-class research and development organisation, and it's been around for 75 years now. It's a membership-based organisation, So our members include most automotive, aerospace, space, gas and power generators. So people like BAE Systems, Airbus are members of TWI, and we have 4 business groups. So those include materials, non-metallics, non-destructive evaluation, and joining, which is where I sit. And I sit in the friction and forge section. So I have not been around as long as Jane, unfortunately. But before I started at TWI, I did a PhD in materials engineering, and we looked at using friction welding for aerospace applications. So normally my day-to-day job at TWI, we essentially just develop solutions to engineering challenges. So that's the usual of increasing the quality whilst reducing the cost, the time, and the price. So I'll just try and introduce you to the process, and I'm sure everyone can jump in at a later stage. But essentially, when we normally talk about welding, we're talking about a fusion welding process, which is where we're melting something to join 2 parts together. In friction welding, it's actually a solid state process. So there's no melting of the material and no consumables involved. The heat is actually achieved by using a combination of motion and pressure. So today we're focusing on rotary friction welding, which, as you'll have seen in the video at the beginning, uses 1 part rotating and 1 part held stationary, and you apply a pressure between those 2 parts that creates heat and allows for plastic deformation of the material, and those 2 parts to be essentially forged together. There are other types of friction welding, including linear friction welding, which uses, instead of a rotating motion, a reciprocating motion, so essentially a up and down movement. And these processes have been actually around a really, really long time. So the patents were initially introduced in the 1920s, and development mainly was undertaken in the 1950s into the 1960s, and TWI were heavily involved in that stage of developing the process. And then machines started to be built for industry towards the end of the 1960s, and again TWI were heavily involved with Thompson friction welding at that stage. So quickly, some advantages of the process, and most of these come due to you not melting the material and it being a solid state welding process. So that gives you high integrity. It results in a fine grain microstructure, which we'll touch on later on, but that tends to give you better mechanical properties than you would get from a fusion welding solution. You don't use consumables. Because there's no melting, you can join materials that are generally classified as unweldable or dissimilar combinations that can't otherwise be joined. Typical ones include aluminium to copper, steel to aluminium, and we'll touch on those later as well. So it avoids defects produced by the melting, so solidification, cracking, or pores that you normally see, especially in materials like aluminium. It's a self-cleaning process, so you might have seen, and you can potentially see in the image behind me, that as you rotate the part and join them together by applying a pressure, you actually get a flash in the material. That's kind of a removal of some of the material in the center. So if there's any oxides or defects in that area, then they're removed from the joint line. And then there's also advantages of the machines and how we make this process work, which I think is a good topic for discussion. So it's highly automated, so everything we do is not by a person, that's just by a machine. And it's really, really quick. So these welds can take between a second and 15 seconds. So it's really good for high productivity. It's very repeatable, again, because you're using an automated machine. The process is the same every single time, and that gives you really good high repeatability. And then finally, I just wanted to mention that it's great for making near net shape parts. So say you have a much wider part with a bit of a lug that sticks off there, and rather than machining that from solid, you can use rotary friction welding or linear friction welding to add components to that larger body, which reduces the amount of total material that you need to use. And because it's a solid state process, it's more like a forging process than a welding process. You don't need to worry too much about those material properties in that welded area. So I'll pass back to Andy, but if anyone has any questions on that, I'd love to discuss it.
Thanks, Kate. I think I'm probably going to take over from you now to talk a little bit about the machines really and the applications that we see with friction welding. I'd like to just take the opportunity to thank Kate for participating in this discussion as well from TWI, and also actually John will join us in a bit from American Friction Welding. As Kate alluded to, we've worked with both TWI and in fact American Friction Welding very successfully over many years, and we value the partnerships that we have. I wanted just to quickly touch upon, if I can, the sort of Thompson KUKA situation, because you'll hear both Thompson and KUKA touched upon quite regularly. I think Jane did explain that KUKA actually purchased the Thompson brand of machines going back to 1993. But just to give it some context, both brands have been kept under KUKA. We weren't rebranded as KUKA, and in fact, essentially in Germany, KUKA would build the KUKA brand friction welding machine, and in the UK, obviously, we build the Thompson brand friction welding machine. And you might actually ask, why is the two brands? I mean, essentially, it's really the way that we've kind of developed with the applications that we see. And I think, obviously, KUKA, again, as Jane touched upon, is kind of known primarily for automation. That's their core product. So we're talking about robots. Obviously, a big market for robots historically has been the automotive sector. And I think consequently, KUKA friction welding has kind of naturally developed into that sector. And consequently, the machines that we would build in Augsburg in Germany are, fairly much aimed at those applications. We've obviously talked about, friction welding is very much the choice for joining safety critical components. And again, I think as Jane put, you get in your car and you're coming into contact with a lot of friction welded components. You might not see them, but things like airbags, engine valves, pistons. I know Jane went through a big list of components. And historically, probably a lot of those components would be perhaps welded on a KUKA machine. It's a bit of a grey area because effectively also Thompson build in the UK a range of machines. Historically, we've gone down to building an 8-ton machine, which in fact, I think, John, you're still the proud owner of that machine, that 8-ton machine. But what we've also been known for at Thompson is building open architecture machines that are able to sort of cope with very, very long components. And again, going back to the requirement to use friction welding as the joining method of choice for certain applications, we look at something like a drill pipe, for instance, that the American Petroleum Institute, the API, will require friction welding to get certification to manufacture drill pipes. So if you're making a drill pipe to API certification or other certifications around the world, then friction welding is the process that needs to be used. So Thompson machines, as I said, typically open architecture. We see a lot of applications for machines that we're building in the oil and gas and the exploration industries. We have machines in build here at the moment in Halesowen in the UK for drill rod applications. And another very, very big area for us historically has been sort of construction machines, where we've built machines for friction welding, sort of piston rods, for example, for hydraulic cylinders. And we're very fortunate that over the years we've got a very good reference list of customers, some of the very, very big OEMs globally for those particular applications. So the solutions that we build in the UK have tended to, we've focused on those specific applications, and we've configured machines to suit that. And we've developed work holding solutions for our machines that make utilizing the machines easy for the customer. So that can be our own design chucks, for instance, for piston rods, would be an example where we've developed a 2-jaw chuck, which we would implement on those machines. But I think John, again, in American Friction Welding will attest, John has quite a few Thompson brand machines. And I think John will explain a bit later on. I mean, John uses them for a lot of different components, not just the ones that I'm mentioning. I mean, really, essentially, they are suitable for the whole range of components. But as a group, as AWS, Advanced Welding Solutions, we will tend to look at what is the best machine, be it a machine that could be built in Germany or be it a machine that could be built in the UK. And really, that's what we'll offer. If a customer comes to us with an application, perhaps wants to buy a solution as opposed to use subcontract friction welding. I know the primary focus of this meeting is to talk about rotary friction welding, but in the advanced welding solutions area, we also build friction stir welding solutions. And again, given the sort of legacy of the company, they're robotic-based friction stir welding solutions. And we're also involved with magnet arc MIAB welding as well. So we build solutions for that as well. So we've got really a wide variety of machines. Typically, we will look at an application that a customer brings to us, and we will configure a machine to suit. But as I say, we see a lot of repeat applications, which I guess is testimony to the machines that we build and the fact that the customers like them and find them good to work with, easy to use and accurate. I guess one other quick application I'd like to touch on is something that really, because the very core at Thompson is the axle machines that we build. And here in the UK, I mean, we go back to 1963, which I can actually tell you is exactly 58 years ago. And I know that because I was born in 1963, but that's actually when we started building friction welding machines over here. And really the initial application that we looked at was truck axles. And consequently, we've developed a very strong solution for welding both truck, trailer axles and drive axles. And effectively, this is a double-ended friction welding solution where we're going to be welding spindles onto the axle housing, and those can these days be pre-machined spindles onto the axle housing simultaneously. And again, I think as Kate suggested, the process is a very, very robust, repeatable process. And part of the solutions that we work with and offer, they have as part of the solution we offer, it's our own software that we've developed specific to the machines. And I think the important facts to say about that is that, the feedback that we get from the market is that it's a very intuitive offer. The software is as easy or as complicated to use as you want. You have different sort of levels that you can set on that software, but it offers total traceability on the welds. You're monitoring those welds in real time, the key parameters that we need to look at. And it's inbuilt quality control in the process in terms of if the parameters that we're monitoring, if some of those are out of kilter with where they should be, the machine will alarm and tell you that. So, you know, there's sort of inbuilt quality control in the process as well. So I guess without going on too long, I think I've probably hopefully given you a bit of an idea about the sort of solutions that we offer here at Thompson KUKA, the types of machines and some of the key application areas we work with. We'd obviously be delighted to talk to you more about that. And I'd welcome any questions you have about the machines as and when you want to ask them. And what I'm going to do, if I can, is I'll hand over to John.
Can I just interrupt there, Nick? And
yeah,
there's a couple of things that you've picked up, which I think are really quite interesting. And also we've had quite a lot of questions coming in, many of which are quite specific, and we'll come back to those a little bit later on. And I see that some of them are being answered in the chat, which is excellent. We might even be quite close to selling a machine by the looks of it, which is great. But there's quite an interesting general question, which I thought maybe we could pass around to everybody for their comments, and that is from Erkan, which says, what do you think are the issues that need to be developed in friction welding technology on machines today? Perhaps if you could quickly start on that, Nick, and then I'll pass it round the panel for their comments on that.
Well, yeah, there are several different things that we're looking at with the friction welding process. I mean, I would always say, Andy, when I talk to people about friction welding, you know, the process itself really hasn't changed greatly in the 60 plus years that we've been building machines. And I think what has changed is the way that we monitor that process and what we do with that data. So, you know, typically, as with a lot of sort of solutions, the advantages have been, you know, the developments in effectively computers, PLCs, control, et cetera, et cetera. So we're definitely always trying to improve that. We're always trying to improve the user interaction with the machine. You know, it could be, for instance, something I've been pushing for a long, long time is, I mean, typically the machines, you know, are very, very robust and will last a long, long time. But like any piece of equipment, there are consumables, there are things to wear out, you know, so I'd like to see sort of more interactive service options, for instance, on the machine, because, you know, sometimes there is one friction, it's a unique machine in a facility. So somebody might only have one friction welding machine, and they might rely on that, they therefore rely on that machine entirely. And consequently, I think that's something that we could look at. You know, there are other areas with the process that we look at as well, in terms of sort of hybrid things that we look at with the process. Early days a little bit with that, you know, we've had some very positive results with that, but you know, it's that's something to look at. But honestly, the old phrase of "if it ain't broke, don't fix it" comes to mind, because it is an extremely robust process. You don't want to overcomplicate it, and you know, that's kind of where I'm coming from with it, I think.
Right. I mean, presumably predictive maintenance techniques
Absolutely
are becoming much more relevant to productivity and cost saving.
Yeah, and I think with, you know, funnily enough, I think with the situation we've all had with COVID, the lockdown, et cetera, I mean, all of our machines, you know, we're an international company, so our machines are installed all over the world. And, you know, if we sell a machine, obviously that, you know, dictates an engineer will have to go out and support the installation of that machine. And then, you know, from time to time, those machines require service. And I think the COVID situation has been a challenge for our customer service department, but equally, I think it's an opportunity to look at ways that we can, you know, we can make the most of the technology that's out there, you know, be that I was talking, I've got to give credit to a colleague of mine who I was talking to last night, Mr. Blanco, about this, but, you know, certainly things like VR glasses, etc., is something that we can think about so that you equip the customer with them and support the customer in maintenance like that. So there's lots of opportunities there. I think.
Yeah. Jeff, you've been very well behaved and quiet up there in my top left-hand corner. Is there anything you'd like to chip in with on that at this stage?
Good afternoon, everyone. Thank you for joining. No, Nick has really summed it up. The process has not changed much in the last 60 years, Nick.
Yeah, exactly, Jeff.
The benefits are there. We have developed, as controls have become more sophisticated, we typically, I mean, I've been doing some work with John recently. We can now hold finished component lengths much more accurately because with sophisticated controls and hydraulics, we can actually tell the parts essentially what length we want them to be. So there are advantages, but no, the process hasn't changed greatly.
There's been a lot of changes in hydraulic controls. We working with Jeff, I was pleasantly surprised on the overall length that we're able to hold. The old style valves, you know, shifting from first friction, second friction, and forge that's drastically has changed now to the point where we're controlling the rate that the slide is moving and how much material we are able to collapse in forge. Thompson has, I think, really moved the bar when it comes to maintaining overall length.
So John, are you talking about there where you're effectively adaptive forge, where you're actually controlling the forge as well? Yeah, the collapse. Yes. Yeah, interesting.
Presumably,
and then,
sorry, carry on.
Well, and the other thing is the motor drives. You know, since the 50s, you know, we didn't have the motor drives that we have now, and we're able to control the deceleration. So now we basically have a hybrid inertia versus you know, the regular you know, direct drive, which is stopping the spindle as quickly as possible. So yeah, I've seen some really good advancements just in the last 5 to 10 years in friction welding, and a lot of that is Thompson.
Is it an area where all the machines are hydraulically driven because of the forces involved, or are there electric versions?
Would you like me to touch on that, Nick?
Why not?
Yes, please, Jeff. Yeah, fire away.
Traditionally, the machines have been hydraulic because of the high forces involved. I mean, we perhaps haven't mentioned this, but typically friction welding machines, when they are pushing the parts together, are using forces anywhere between, at the low end, a few tons force, up to, on bigger machines in our range, 400 tons force. And to get the required power density, hydraulics was the optimum solution. Having said that, nowadays, at the bottom end of the market particularly, we can see the advantages of electric drive. We have built electric machines in the past, but I think possibly their time has arrived that if anybody was designing a small, let's say, sub 20 ton friction welder nowadays, they would start with an electric solution.
So it would be similar to this type of arguments with injection molding machines, I guess.
Absolutely, very similar.
Yeah.
Yes.
Yeah. Okay. I'd like to jump to Kate because got a couple of questions for her, really from what she was saying earlier. One is you mentioned that some materials can't be joined by other methods, and I presume that's because of the lack of a weld pool, and maybe with aluminium getting the oxides in the way or of the joint and so on. But I thought maybe expand on that. And also whether you could, I know you're quite keen to talk about the relative advantages of friction welding against vacuum brazing. So that might be an opportunity to talk about that as well.
Sure, I'm not an expert on brazing, but I think I know some disadvantages of it. So yeah, there's some materials where when you fusion weld them, an example that comes to mind is a 7000 series aluminium or like a 2024 aluminium alloy. And when if they're just seen as unweldable, generally using like arc welding techniques or any fusion welding method. I think the reasoning, again, I'm not a fusion welding expert either. I think the reasoning is generally as you solidify, then you get cracking and you get pores forming within the material as you weld it. And often you have to use a filler material, and that's the case in brazing too. So although brazing can be used to join some dissimilar materials, you're not melting the parent material, but you are melting a filler material that's generally softer and not as strong that you use to join those materials. Whereas in friction welding, you're not doing that. So you're not having to use a different type of material. So joining aluminium, for instance, rather than having to use that softer aluminium alloy to join the two materials, which might be incompatible with the strength needs or other requirements that you have, like corrosion or something else that you have as a requirement within your component, that filler might not actually meet those requirements. So in friction, you're able to just remove that altogether and not use any kind of filler, which might be a lower strength and also a different alloy.
Great, and I guess
oh, sorry, Andy.
No,
Jeff.
That might be something you'd be interested to talk about.
Kate, so to sum up, I think we can just say fusion welding is a way of deliberately introducing defects into a material.
I was trying to be PC, Jeff, but I'm.
That sounds like a great quote that we can take forward. And one more question that we actually got when we first sent out the promotions for this. So we have answered it, but we've got a new audience now, so maybe we should answer it again. Is how capable would friction welding be to join a tube to a plate, and what would be the issues there?
I can answer.
Go for it. Yeah.
So essentially, that's quite easy to join a tube to a plate. I think we've probably, I'm sure, I feel like Jeff's just gone to try and find something that joins a tube to a plate.
He's got a wealth of samples in that basement.
There he is.
There we go. Yeah, so it's actually really good for joining things like adding a flange to things as well. So adding any kind of component. So the limitations of rotary friction welding are generally that it has to be kind of round or cylindrical. But in terms of if you use linear friction welding, then that actually allows you to use other shapes and sizes of components. So you could join a square tube to a round plate, for instance, if you were to use that.
Great. And on cue, there's a question just come in from Ben, which is there much debris created during a friction weld, and how do you deal with it during an automated process? So who fancies that one? Maybe that's one for you, Nick.
Yeah, so I guess really the actual friction welding process itself is relatively clean. Indeed, with a lot of friction welds, there isn't necessarily fume extraction on the machine, for instance. That can be an option that's fitted on the machine, but in general terms, yes, you get a bit of heat, but it's not a dirty process in any shape or form. I think the time when you get some debris coming off the machine is when we remove the upset or we flash remove. And there are several, sometimes if it's a tube-to-tube geometry, for instance, we might also want to take the upset off on the inside. because there might be a requirement to have a clear path through the tube as well. So we have, on the machines that we offer, we've over the years developed quite a few different methods for removing that flash or upset. And perhaps two of them that we'll talk about are where we're taking that external flash off, where we either simply turn it off, as I think was shown in the video actually at the start of the presentation. And obviously that's going to give you some material that comes off. Again, typically the machines are designed in such a way that when we've got that process going on, as much as possible, we try and guide that swarf or flash into a sort of a hole, if you like, or in the bottom of the machine, and we'll take that away, and that can go on to a swarf or a chip conveyor, and it can be shredded as well. We can put a shredder on the end of that conveyor, so we control that as much as possible. You know, flash is always a bit of a challenge. And I remember selling a machine or some machines to a certain company in North America that make green machines that go around in fields, which will probably narrow it down a little bit. You know, and that was something that they were very keen for us to control as best as possible, because if you've got, you know, hot flash flying around, it's a problem. So I guess that's you know, that's about the most that you're going to get, really. Jeff, you any other thoughts on that? And well, actually, John's probably good to comment on this.
I was just going to comment.
Welds all day long.
On the, you mentioned fume removal.
Yeah.
The friction welding process itself, with the majority of metals that we weld, does not produce any fumes. But typically, the customers will have parts that are covered in, say, oil or grease. So when you friction weld them, they get hot and that oil or grease vaporizes and causes fumes. The friction welding process itself doesn't generate fumes.
And I like to point out, as a subcontractor, some of our machines do have flash removal at the welder. We typically don't use it unless we really have to, because the swarf is hot when we're flash removing after welding. It's hot. It flies around. It can land on electrical cables and hydraulic hoses, and we do what we can to protect those. But typically, we'll allow the part to cool, and then we'll remove the flash on a much less costlier machine. It will, that way it allows the friction welder that can tend to be, you know, hundreds of thousands to millions of dollars. Let it do the welding as quickly as it can. Then after the parts are cooled, we can have 1, 2, even 3 CNC machines just removing the swarf afterwards. Tolerances are generally held better, and you know, we just don't want a $1 million friction welder waiting for an insert to be changed. So it's better to do that on a $50,000 or $50,000 CNC machine that has 7 turrets, and you know, they change the inserts once a day.
Sure.
Brilliant.
Sure. Jane, are you still with us? Do you want to sort of comment on that as well?
Well, for most of our jobs that we do in subcontract, the flash is always taken off by the machine. We do use the machine for this where possible, just because we don't want to use another body on a lathe separately. We try and keep as much on the machines as possible. In my case, I have a limited footprint, so you know, for me, I need to keep everything within the department rather than using lathes that are out of the department. But we don't have a huge problem with flash. Nearly, I would say, well, with copper and aluminium stuff that we weld, we don't flash remove that, and that is the vast majority of the stuff that we weld at the moment. Anything that is ferrous, we tend to flash remove. That accounts for probably 30% of our subcontract work. And we, you know, it's the machines are cleaned out daily at the end of every shift, and we don't tend to see a huge problem with keeping things clean and all the problems that John's mentioned, actually. We don't have the problems with the swarf flying everywhere, but then the guarding's been modified on our machines to ensure that, you know, everybody's safe and that they've been kept in, the flash is kept in, because we use it all the time.
Yeah, it's interesting. I mean, I've heard both sides of the story on many occasions as well, going to talk to customers, what John has alluded to, you know, some customers feel exactly that. And, you know, I don't want to use that, as I think John said, I don't want to use that asset for removing flash. And then obviously on other occasions it is used, you know. So we see a mixture of requirements, it's fair to say, I think.
Also, my ultimate boss doesn't like to see the machines not operating fully. We're pushed to do as much on our machines as possible.
Yeah, I should imagine a lot depends on individual business and component circumstances as to which is the best way to go, doesn't it? So, so I'm sure they both have merit. We're getting lots of questions coming in on specifications and also testing, which I think we'll take when Jeff speaks in a moment, following his kind of run through the metallurgical side. But hopefully the discussion so far has whet everybody's appetite to hear a bit about making the business case for the process. And this is always one of the most difficult things to get your head around, I find. And, you know, there are options for capital investment or subcontract. And so John Fisher is now going to take us through that process of how you make the decision.
So I've been tasked on to answer why and when subcontract versus capital investment makes sense. And we are a subcontract machine shop, friction welder. Friction welding is our core competency. And really to answer that question, it has a lot to do with the volume of the parts that you're doing. Again, these are expensive machines. So if you don't have to buy the cow, you can just buy the milk. And so what that allows us to do is, if you don't have the volume, you can't run these machines, you know, 8 hours a day, or, you know, maybe it might be cyclic. Maybe, you know, in the fall, you might have a lot of volume, and then the machine would sit for a long time. We're experienced in the process, and we make, you know, our job is to ensure that the process is kept locked and fixed. It's done the same way. Setup notes are made, parameters are locked and fixed, and we want to make sure that every part is good. So a lot of our machines they may have 5 or 6 different setups during the day, because we have a number of customers. We are also backups for companies that have their own welders. They may have, you know, one welder that could be welding, you know, 2 shifts a day, and you know, something goes down on it, then, you know, they need, or there's a supply chain issue and they can't make that up in time, then that's where we help out. Again, making sure that the process is followed the way it's meant to be followed. Some OEMs, original equipment manufacturers, they want to focus on what they're they don't want to you know, learn about a destructive, non-destructive testing. They don't want to learn you know, specifications. They want parts to come in, assemblies to come in, ready to go, so that they can assemble them. And that's where we fit in. But I mean, it really boils down to is the cost of the machine versus, you know, the volume or the amount of runtime you think you're going to be running that machine.
John, I think perhaps it ought to be mentioned that even some customers whose volumes can justify a machine purchase would still rather deal with somebody like you, because friction welding is such a niche process that a lot of customers aren't that comfortable with it. You know, they don't have come across it before, so they're happy to give it to someone like yourself, who they know, you know, are experts in the process.
It's true. Thank you. I've also been tasked on, you know, where we can get help from. Obviously, Thompson and KUKA and EWI, they're great sources. I lean on Jeff a lot with different things, but American Welding Society is a good reference. They have a specification of recommended practices for friction welding, which is C6.1, and then they have specifications for friction welding of metals, which is C6.2. Jane had mentioned one of the comments, the ISO standard, which is 15620. ASME also has a boiler and pressure vessel code, which is section 9. That's a very difficult one to follow, but we do use that from time to time. And then there's a mill standard, which is way out of date. I think it's 1975, 1252, mill standard 1252, which is the inertia friction welding process, procedure, and performance qualifications. We do follow a lot of AWS when it comes to destructive testing. I was going to answer this in one of the chats, but I think it's better if I just explain it. AWS B4.0, which is Standard Methods of Mechanical Testing of Welds, is a great resource on bend tests, tensile tests, all the different applications that that a weld could be tested. Is a real good source. Also, AWS B2.1, which is a specification for welding procedures and performance qualifications. So those are the ones that we use just to give the comfort to our customers that our weld is or the weld is going to meet their requirements.
Thank you, John. One of the questions that I often ask in these sessions is when we're dealing with a fast-moving technology where the technology is ahead of the specifications, which I kind of wouldn't have expected with friction welding, because as you've all explained, it's been around for a very long time. But I noticed that the 15620 was revised in 2019, and I wondered what had changed to encourage that reissue.
I can answer that a little bit. They've added in friction stir welding and other types of friction welding into the standard, and that explains most of the changes, really.
So nothing's really changed in terms of the process that we're talking about.
They have added in they've added in some additional kind of like qualification testing for safety critical. They've categorized safety critical components and the types of tests that you could possibly do for those. They've included more non-destructive testing than I think in the previous standard, although for friction welding, non-destructive testing is not necessarily the right way to test, because the things that you're looking for with, say, ultrasonic testing, the discontinuities just don't occur in friction welding. So I don't know how valuable it is, but anyway, it's been added, and if it gives somebody who's making safety critical components comfort, then that's what you do.
Yeah. Where Bo has just said in the chat, is it possible, John, for you to type in the different standards in the chat? I know you've done some of them, but you have mentioned some others and embellished what you're going to say about them. So if you could put those in the chat, that would be very much appreciated, because then that can be a good reference source for everybody that's attending. Coming back to the issue of subcontract versus capital expenditure, how much of a role does the size or shape of the component influence that decision? And obviously the volume of manufacture would do as well, wouldn't it? So how do you compute where the crossover might be, if you can?
Thankfully, as Nick had indicated, Thompson and KUKA do make a range of machines that go from very small to a 4-ton machine where where the tooling can go down to, I believe, 2 millimeters, 80 thousandths, up to I have a 250-ton machine that can go about 6-inch solid, maybe 6.5, depending on the material. So that is our range. And then they have the open architecture machines that what I call unlimited length, because if you have to, you could knock a hole in the wall and have a railroad stop out in the parking lot, right?
Yeah, absolutely.
So yeah.
Don't joke. We actually did that, I believe, in the UK, Jane. Didn't we knock the wall down between two to get a part in?
Yeah, I've heard it being done.
Yeah.
So yeah, and then there's different support equipment, might be induction stress relieving, flash removing in a lathe or something like that. But they're size is of the machine is definitely a factor of what can be welded.
Yeah, sure. I think I'd add into that as well is that and this kind of touches a little bit upon what John talked about earlier on in terms of levels of control of the machine, the hydraulics, et cetera, is the capability of the machines, a specific machine to weld a range of components as well. So if a customer has a big range of components that they want to put on the machine, obviously all of that adds to the justification in buying a machine if that's their chosen path. So typically since I've been at Thompson and Jeff and I'm sure John will see this as well with the machines that he's acquired over the years, that the range, the capacity of the machines has increased. So that's one way the machines have improved. And in terms of making a case for a machine, that's very important. That's very important. And I think also John touched upon sort of, in his business, he does numerous changeovers every day on his machines. And that's an area I think that we've also paid a lot of attention to over the years here is the tool changes, because, if certain, you go back and you look at certain types of machines and the tool changeover times can be, half a day, if not a day on some of the bigger machines. Whereas that's something that we've paid a lot of attention to, and quite often, it can be as part of a contract where the customer says, we want a worst case scenario on a tool changeover, so that can be something that we're tasked with as well as with supplying a machine. But all of that, of course, factors into the case for a customer to make. Could be automating the machine, obviously that's another factor as well, getting those parts through quickly.
Yeah, so lots of factors, and I guess has to be treated on a case-by-case basis, really, doesn't it?
Absolutely, yeah.
Some of our machines have 5 or 6 different setups per day. There's machines that have been running the same part since 2008.
Yeah, I think one of your machines, John, if I remember right, it was that 15-ton machine that I know and love. How many parts?
7 million welds. 7 million.
7 million welds. So do you think, has that paid for itself, John?
I think it has.
Good.
Excellent. Well, there's a question about whether you have a rep in the Midwest, specifically Oklahoma. So you can answer that in the chat and it'll avoid me breaking into song, I think. And instead of that, I'm going to ask Jeff to talk about the metallurgical side of the process and how the metallurgical laboratory contributes. We'll talk about product and weld integrity, bimetallics, which we've touched on already, and then perhaps just lead into some discussion about testing processes as well. Over to you, Jeff.
Well, I suppose I ought to introduce myself. Jeff Price. I'm the manager of North American operations for Thompson Friction Welding. Just briefly, Nick mentioned that we make friction welders in Germany and the UK, the KUKA and Thompson brands. I'm responsible for the Thompson brand in the UK. I'd like to say at the outset, I'm not a practicing metallurgist. So if I screw any of this up, please forgive me. One thing I don't think we sort of really dwelt on yet, one of the great advantages of friction weldings, Kate talked about, you know, the advantages in terms of fast cycle time, the ability to weld bimetallic joints, no consumables, no fluxes, no gases. But I think for the majority of my customers, 95% of whom are just welding two pieces of steel together, the biggest advantage is the terrific robustness of the process. Comparing it to, let's say, arc welding, where you have to have certified operators, laser welding or electron beam, where, you know, you really have to be careful about getting the alignment right. You have to prep the ends of the parts. With friction welding, you throw two pieces of steel into the machine. You don't have to clean the ends. You don't have to prep them in any way. The operator presses the button and you get a good weld every time. John talked about nailing the parameters down, and he does, because that's the right thing to do. But the truth of the matter is there's three essential parameters in friction welding: the rotational speed, and the amount of force you use, and the amount of material you burn off. And if you're welding two pieces of steel, you can vary any of those parameters within over 50%, and you're still guaranteed a good weld every time. And I think that's something that we haven't dwelled on yet, that even when you don't do everything right, you still end up with a high integrity weld. So that is one of the great advantages of friction welding. On the metallurgical side, I'm going to confine myself mainly to steel, because again, that's the most common application. And although friction welding is very simple, in as much as you are just taking two pieces of steel, rotating one and pushing them together, what happens within that heat affected zone surrounding the weld can be quite complex. You're taking a piece of steel, heating it up to its melting point, or just below its melting point. As a result, the steel will transform from ferrite to austenite. It will then cool after welding. Now, depending upon the material, exact material composition and the rate of cooling, you are quite possibly going to get some hardness in the weld. In some applications, this may be insignificant, but I do have customers who are welding, say, piston rods, where they're using a 1045 steel, and after welding, they can get hardnesses of up to 55, 60 Rockwell in the heat affected zone. Some applications that's not significant, but in some applications you are going to require post-weld heat treatment. If I can just say, that's not related to friction welding per se. Any joining technique you use where you heat the materials to near the melting point and then cool them will, you know, have the same problems. Kate talked about getting a fine grain structure. The actual grain structure will vary through the heat affected zone. During the welding process, as the material heats up, you can possibly see some grain growth. At the end of the weld, you forge the materials together, which can actually cause some grain refinement. And you will also see the direction of the grains in the steel changing due to the flow pattern of the material during welding. So you can get some quite complex structures in the heat affected zone. But again, a lot of it is not specifically related to friction welding. It's just due to the fact that you're heating and cooling materials. John, on that, how much of your product do you need to post-weld heat treat?
Well, we post-weld heat treat anything with the high alloy and high carbon. Definitely want to stay away from a brittle weld. In fact, a lot of the specs will call out for no brittle phases. So when we do a metallurgical evaluation of a prototype weld, we're looking for no voids, no cracks, no brittle phases. And we basically leave it up to our customer as what hardness they would require. However, a lot of customers don't have a requirement, and at that point, it's best to put a part in the field for several months, or do some sort of accelerated fatigue testing to verify that the joint is ductile and sufficient.
How about you, Jane? Do you do much post-weld heat treat?
Yeah, we do with certain product types. So drill pipes, we always post-weld heat treat drill pipes. We do a stress relief on them after welding. So we take them up to 650, make sure they're fully soaked, and then they just air cool, and that's sufficient to take out any stresses that the heatings put in there during the friction welding process. We weld quite a lot of piston rods, but we don't do any post-weld heat treating on piston rods. And obviously we're using the same materials, but the yellow goods manufacturers that we weld for, they friction weld themselves, and we do quite a bit of overspill work for them. And they don't do any post-weld heat treatment on their own production either. So that just seems to be like an industry standard. I don't know whether it's the service life of the components slightly different. I mean, with drill pipes, you'll see a lot more. I would imagine that the stresses that those components are under in their service life are much greater than a piston rod would be, because some of them are used in percussive, rock drilling, that kind of thing. So it just depends on the application as well, I think. As John said, if you can do some fatigue testing that it kind of matches your application, then you've got a much more sort of like realistic view of what you need to do if there is any post-weld heat treatment required.
I have to add, I've not met a metallurgist that said don't post heat treat. They always want you to put it in an oven and remove the stresses. There's never anything wrong with doing that unless in a chrome plated bar application, you're going to destroy the chrome plate.
Right. Yeah.
Kate, can you comment on that?
As a metallurgist,
yes.
Normally you can always improve the properties using a post-weld heat treatment, as long as it is a predefined heat treatment and not something that's just going to absolutely completely destroy your base material. But as Jane said, it doesn't and Jeff, doesn't always have to be the case that you post-weld heat treat something.
Fit for purpose.
It's often that you can get a fit for purpose part with it as welded in the as welded condition.
Sure.
Sorry, Nick. Again, the hardness becomes a property with a problem with the higher carbon or the alloyed steels. A lot of our applications are relatively low carbon steel, where hardness is not an issue.
Yeah, it really depends on the material that you're using and the application. So most of the time, if you're using something for aerospace, for instance, you'd normally use a post-weld heat treatment, and those might be titanium parts, nickel superalloys, or the kind of higher carbon steels. Yeah,
we have been asked a question about what are the points you might pay particular attention to regarding the friction welding of titanium parts. So I guess that's part of an answer. Are there any other issues that titanium would present?
Probably depends on what you're welding it to.
Yeah,
Well,
if
yes,
it's welded to itself, it's a relatively easy weld.
yeah.
And to aluminium.
Well, titanium to titanium is quite nice and easy to friction weld. If you're joining it to steel, for instance, that can be a little bit more tricky. And there's a bit of process development that he's doing there, and thoughts about if you use, so some materials, although friction welding is really good for joining dissimilar materials, some combinations are harder than others. So titanium to steel is not the easiest of combinations, and it can be done, but often you might need to use like almost a layer of something in between. So you might put a slightly different alloy in between the two, friction weld that, and then almost completely eradicate it by joining the second alloy. So you might end up with a 0.2 millimeter thickness part section in the middle, which is a slightly different alloy between the titanium and the steel. But generally, titanium is pretty easy to join to each other.
Yeah, we commonly weld titanium to 6063 aluminium to stainless steel. That's a very common joint for us to make, with a very, very thin interlayer between the stainless steel and the titanium.
So
does using an interlayer sort of make the process less attractive relative to other processes, or not?
It makes it less attractive compared directly to friction welding without an interlayer, but often we would only use an interlayer where another process can't join that material. So
it's the best possible option.
It's the best possible option. Yeah, I think I'm pretty sure. I mean, maybe I'm gonna look really stupid saying this, but I'm pretty sure titanium steel can't generally be joined using any other welding method. Not easily. Maybe brazing, but you're not actually joining those two materials there. You're using an interlayer there as well. So it can be the best option to join those two materials, unless you're wanting to use something more mechanical. We can actually join some materials using a kind of mechanical fit. So this is really hard to describe without a picture. But if you have a harder material, say, and you're trying to join that to a softer material like aluminium, you can almost forge one of those materials around the other. So forge the softer material around the harder material, and then you end up with a partial metallic joint, but also like partially a mechanical joint, which can often be fit for purpose as well.
That doesn't sound as good as friction welding, though.
It's partly friction welding.
It's partly friction welding. So yeah, it
sounds very interesting. So
this isn't something I can really describe without a picture. But
one more metallurgical question, and I'm conscious of time, but our audience is sticking with us, so we're obviously doing a very good job. Question came in about what is the heat affected zone size of friction welding versus other welding processes? Who
generally smaller.
Yeah. As one would expect.
The heat input in friction welding is directed into the weld interface and is relatively quick, certainly relative to other welding processes.
Thank you.
The temperature lower as well.
Yeah, so you're normally welding at a forging temperature rather than a melting temperature. So the total temperature is lower, so the total heat input is lower, so the heat affected zone is lower.
And jumping back to titanium, is it done in an argon atmosphere, we're asked?
It doesn't, we don't normally use any kind of atmosphere around the parts. So I haven't seen that being done.
No,
generally it's just material to material, so sort of no third party materials or gases.
The theory of friction welding is that the two faces pushed together as the material plasticizes excludes any oxygen from the weld interface. So there's no need for any inert atmosphere.
Yeah, so even if as you form oxides on that surface, they're then removed in that flash. So it's like a self-cleaning process.
Yeah, conditioning kind of process. First friction.
Should we say something about?
Sorry, John.
Something about sulfur and lead.
Yes.
Sulfurized materials. We've seen some success, although marginally, with resulfurized materials. Sulfur and lead are something that we've seen to be very, very tricky to weld if the material has it, because we'll end up getting voids when we weld with sulfur. And I don't know if I mean, we try to keep sulfur down whenever possible. What are you guys seeing?
Well, we generally ask for not to have free machining materials for friction welding for that very reason, because they're difficult. Yeah,
we've done that. We've done some free machining that has resulfurized materials in it, but we do a lot of then the non-destructive testing with ultrasonic testing.
Yeah.
Sure that we don't have any voids at that weld interface, and we can see some lower yields when using the free machining materials.
I think going back to a point somebody made earlier, I think unique, about the product being fit for service. I have friction welded free machining steels, and granted it's not perfect, but if the weld joint is 70% the strength of the parent material, that is more than adequate for a lot of.
It is fit for purpose. Yeah.
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 Okay, and yet another question come in. Back to interlayers, what kind of material and thickness would be used for the interlayer?
Well, generally you use interlayers where you're welding bimetallic materials. So the first consideration is you'll be welding two materials, titanium and aluminum, titanium and steel, and they're going to have very different coefficients of expansion with temperature. So you heat them up to nearly their melting point, they get nice and hot, they expand, then they cool down, and of course the amount of contraction when they cool is going to be different in the two materials. So then if you just weld them directly, you're going to be introducing stresses into that weld joint. So one of the purposes of the interlayer, typically aluminum, is to have a ductile material that can absorb those stresses. The answer to how thin is it? As thin as you can get away with. It isn't a very good answer.
You still have to hold on to it. You still need tooling to hold on to it.
Yes.
Yeah, so you'd start with a longer bar that you hold on to with your tool, and you join that, and then you'd cut that down and machine that away, and then because it's a process where that flash and that material is ejected, you get some removal of material. So if you develop the process perfectly, you can develop it so that you get rid of almost all of it. So you're left with a really, really thin interlayer.
Okay,
but essentially the answer is it depends.
Okay, one more question on this. Sorry, go on. If you go.
No, I was going to say there is one other problem that we've not touched on with dissimilar materials, is that you can get the formation of what are known as intermetallics in the weld interface. So typically titanium, aluminum, sorry, I forgot my audience, aluminium. If you friction weld those, they will tend to form an intermetallic compound of titanium and aluminium. And unfortunately, those compounds are typically quite brittle. So if you get any significant thickness in the weld, it can make the joint brittle. Strong, but brittle. And I don't have a lot of experience in it. Kate might be able to talk better, but sometimes by using an interlayer, you can have a material that's compatible with the two materials on either side, even though you can't weld those materials directly.
Yeah, can I just go back there? You mean titanium and stainless steel, which is where your intermetallics grow?
With lots of different materials. Titanium,
because we use the aluminium as the interlayer to prevent the issue with the intermetallics between the stainless steel and the titanium.
But what we tend to use is pure aluminium. So rather than using an aluminium that has alloying elements in it, we try and use pure aluminium, which doesn't form those intermetallics with the other materials. But yeah, Jane, the hardest combination tends to be titanium to stainless steel, and that tends to be where we get intermetallics forming. And that's why we would use an interlayer. Where we don't get those intermetallics forming, we can just directly join the two materials to one another. And I think we've kind of gone off track a little bit, because for the most part, and actually friction welding can join more combinations of material than any other joining process in terms of welding. So any fusion welding process, friction can beat those in terms of what materials it can join together. There's just a few materials where we have to be a bit cleverer in how we approach them and how we join them together.
Yeah, good point. But it's always good to talk on the edge, isn't it? Because
where
the exciting developments
what Kate is saying is that okay, with friction welding, it might be a little bit difficult. With any other process, impossible.
Yeah.
Yes,
yeah, absolutely. Yeah.
Excellent. Well, you've handled that bit very well. I think, bearing in mind the time, I'd just like to do one last topic, and we'll be brief if we can, and that is testing and validation. And there are 3 questions that came in, so perhaps we can take them all in one go. What are the minimum testing requirements for quality and code verification? Is it bend tests and tensile tests? What kind of flaw detection or materials abuse inspection is recommended for friction welding sections? And what about radiographic and hydro pressure load testing? So there's a collection of questions. Let's start with Jeff, and we'll work through all of our experts, and then we'll wrap up. I think we've covered everybody's question pretty much in the chat. Jeff.
Yes, in the AWS standards, there are some recommendations for testing, and it goes through almost like a risk assessment, where it says, how often are you welding these, how important is the weld, so on, to determine an appropriate level of testing. The problem with friction welding is, because of its nature, because it does produce a full face homogeneous bond, that you don't get the typical defects that you test for in other welds. So any kind of surface test looking for cracks isn't really relevant. Ultrasonic can be used, but generally you are actually picking up material defects rather than defects in the actual weld itself. And by far the most common form of testing for friction welding is destructive testing. Now, the obvious problem with destructive testing is you can't do it 100%, because otherwise you'd have no parts left. So typically, most manufacturers will run a part at the start of a shift. Some people, the start of a week. They will weld a part, do a destructive test, bend test, possibly some companies a tensile test. And if they're happy with that, they keep on welding.
I'll point out, Jeff, that when you're doing destructive or non-destructive testing, we do that mainly to verify the material, because we have such confidence in the process. The welders monitor themselves for pressures, RPMs, displacement, RPMs. So if anything falls outside of a window that we've set, it's gonna fault out. And generally, if we do destructive testing or ultrasonic testing or non-destructive testing, we find an issue after it's welded. It's generally because there may be a stringer in the material. We may have a bar was mixed in improperly at a supplier, but that's where destructive testing and non-destructive testing will help out.
I think John's making a really good point there, is that what we normally, when we're testing, so doing mechanical testing or non-destructive testing, microstructural testing, that's all normally done at the process development stage. So what we really do at TWI, developing a process from scratch and making sure that it works for your certain material combination. Once you're actually subcontracting this work, or you've bought a machine to run this process, it's normally a batch test. So you might test one every 100 parts, or one at the beginning of the day, one at the end of the day, and normally the machine will follow the process for you. So like John just said, that's checking that every single weld is coming out exactly the same, and it's very, very reliable. So we generally trust that that means that every weld is exactly the same if the material inputted is the same.
Excellent.
Okay, Nick, any comments?
No, I think these guys have just sold it for me really here. That the process, as they say, is exceedingly robust. The traceability, monitoring those parameters all the way through the rotation, the forge force, and the displacement. And if there is an issue with the material, as John alluded to, the machine will tell him actually before he has to embark on his testing. He'll potentially know he's got a problem. And in terms of the machines these days, with storage, etc., you can keep all of that data of the welding that you've done, and you can choose to download it to an external server, etc., etc. So it is, it very much monitors itself.
Thank you. And Jane, any further comments?
Well, when we take in new work from or new product from a new customer, we tend to write a weld procedure specification, where we'll do kind of a band test approach. So we'll do like a high, low, and mid parameter, and we'll bend test them. We tend not to do any non-destructive testing ourselves. If it's required, then it is feasible to do it, but usually we'll send that out for somebody else to do that for us. But once the weld procedure specification has been confirmed, it just really depends on the customer, the value of their component, and their sort of like application, how safety critical it is, as to how much testing they require. We have some customers that say, right, okay, you've done the weld procedure spec. We know that the process is very repeatable and robust, so they don't require any further batch testing, although that's not something we at KUKA would recommend. We prefer to do a first off batch test on every batch of components that we weld, because that's an insurance policy for us and the customer. If they get a rogue batch of material, then we'll notice this if the material's burning off more material than expected, or not as much as expected. And that flags the problem up right at the beginning of the friction welding cycle, rather than at the end when the product's in service and then it's bad for everybody. So that's our attitude towards it, really.
Excellent. Well, with that, like to thank all of our panelists who've given us the benefit of a huge amount of expertise collectively and turned a metallurgical process into a really interesting 90 minutes. And I thank you all for doing that. And also would like to thank all of the people who've participated as attendees. Between us, we've created a fantastic chat and compendium of information on the process. So I hope that will be useful to everybody. Thank you very much for devoting your time and staying with us for over 90 minutes of a really interesting debate. We look forward to seeing you again for future Talking Industry events, and thank you very much indeed to everybody concerned. Take care. Bye.
Thank you. Thanks, Andy.
Bye.
Thank you.
Thank you.
Thank you.